Hello, AP Calculus kids. Today is day 3 of our review for the AP Calc test, and today we're going to focus on um, how to find the net change of a function using the derivative graph, and we're going to also talk about using that derivative graph to find out when it's increasing, decreasing, concave up, concave down. In the last two questions here, we'll be focused more on the idea of net change to find the answers to those questions. So I want to make this video short and sweet. So here we go. When is a function increasing? When is f of x increasing? If this is the graph of f prime, you would look for when f prime is positive, and that would be on the interval from 0 to, let's say, 5.2. 1, 2, 3, 4, 5, about 5.2. So you would say f is increasing on the interval from 0 to 5.2. When is it decreasing? You would say, oh wait, you always want to justify your answer because f prime is positive. It's above, this curve is above the x-axis. It's positive in that domain. So next thing you want to do is talk about decreasing. So you'd say f is decreasing on the interval, or you could just say on I, and you would say from -4 to 0, because here it's below the x-axis, the derivative is negative, and from 5.2 to about 8, I believe that's 8. This is a graph that I made up just to kind of represent one of the possible functions they could give you on the AP test. When is this function concave up? Well, concave up can be described in two ways. When f prime prime of x is positive, or when f prime of x increases. That's a legitimate reason to give the AP readers. So you would look for where f prime of x is increasing, and that happens on the interval. F is concave up on the interval from, so it's increasing from 0 to, I'm sorry, from -2 to 0, and from 0 to 2. Now you may wonder, why did I break up the interval? It's because there's a corner right here, and where there's a corner, there's non-existence. Where there's a corner on the f prime graph, that means there's non-existence of the second derivative. So you can't really say at that point the function was concave up. So, and you would say because f prime of x is increasing on that interval. Concave down, f is concave down on the interval from from -4 to -2, and from, again here you're going to say from 2 to 4, and the interval from 4 to 8. Now I had to break that interval up for the same reason as I gave before. Because, remember, when you have a corner, you can't have a derivative of that graph at that corner. So that would show a failure for the second derivative to exist at those points where you have a corner on the first derivative graph. Okay, so now we're going to work on our next problem, and that is finding what f of -4 is if we're given the initial condition f at 0. We're going to use the net change theorem to help us do that. So the net change theorem says that if you know the area under a derivatives graph, you can determine what the net change in that function is. As an example, if we had a velocity graph, and I was saying velocity is a function of time, and that would be meters per second, and if I found the area under it from time equals 2 to time equals 4, that area would be the net change in position. Well, this is using a physics analogy, And if I do the integral from, let's say, 2 to 4 underneath the velocity curve is equal to the position at 4 minus position at 2, this is basically our net change theorem. So the net change in position, if you identify the units, time is seconds. And if we multiply, because area is multiplying the units, and we find out by multiplying meters per second by seconds, we get, for this area representation, a unit of meters. So that would be our net change in meters from from 2 to 4. So using the same idea, we want to do it with a generic function. Remember, velocity is a derivative of position, so this all fits up very nicely. I'm going to just rewrite this as the function at b minus the function at a is equal to the net change from a to b, or I'm sorry, the area from a to b underneath the derivative function. So we're going to use that to help us figure this problem out. So we want to find what we have. F of 0 is 5, so I'll just write out we have f of, we're going to integrate from lower limit -4, upper limit 0, f prime of x dx, and we're going to put on this side, we're going to say f of 0 minus f of -4, and if we do our, let me zoom out so you can see the picture. If that's a half circle, so that half circle area will be 2 pi. If the radius is 2, it's a semicircle. So the area from 0 to -4 is -2 pi because it's underneath the axis. F at 0 is equal to, I'm going to replace that with 5, and f of -4 is what's being subtracted. So we'll just solve for that. F of -4 is equal to 5 plus 2 pi. So what that means is at -4, we had a higher value. We had 5 plus 2 pi as our value. And then as we moved along the x-axis, we had a negative area, which was giving back value of the function. So it's actually losing value. So at 0, we're at a lower value than we were at -4. So that's what we end up getting here. For -4, we have a higher value than we had at x equals 0. So let's do the other one. If that's true, then we can find out this area the same way. We can say f of, well, the area from this area from 2 to 0, what does that area represent using net change? That would be the net change in position from 0 to 2. So we have f of 2 minus f of 0 equals the area from 0 to 2 under the derivative graph. Net change theorem works quite nice for these problems. So f of 2 is equal to f of 0 plus the integral from 0 to 2 under the derivative graph. So f of 0 was 5 plus that area, since it's a 2 by 3 triangle, it would be 3. So f of 2 would end up being at 8. F at 0 was at 5. So what this means is this positive area represents the amount of net change in position that we had from 0 to 2. Hopefully this has helped you understand the net change theorem better, and look forward to hearing your comments. Have a good day.